In this video, we are going to work through the first set of topics you'll need to know for your Organic Chemistry 1 class and the first exam. Pause if you need to and try each question. Identify the functional groups in each compound. For the first question, we are going to identify functional groups. Functional will exclude alkanes because alkanes have minimal reactivity in terms of the reactions that can take place. A has an OH group, and this will be an alcohol. B has an SH group, and this will be a thiol. C has a COOH group, which is called a carboxylic acid. And D has an oxygen in between two carbons, which is called an ether. For number 2, we are going to convert the condensed formula into both an expanded structure and a skeletal structure. An expanded structure is the fully drawn structure with all atoms shown, including carbon and hydrogen. Every single bond is drawn, including CH bonds, and it's useful for seeing the exact connections between atoms. For a skeletal structure, also known as a line angle structure, the carbons are not labeled and each bend or end of a line is a carbon atom. Hydrogens on carbons are not shown, but they are assumed to be there to create 4 bonds for each carbon. Heteroatoms like oxygen, nitrogen, and chlorine are always shown along with hydrogens bonded to those heteroatoms. I will start by drawing the expanded structure. For A, I have a CH3 group connected to a CH2, and then CH3. The CH3 in parentheses tells me that it is directly connected to CH in the chain. So far, all carbons have 4 bonds, so we did not have to add any double or triple bonds. On the end, there is a CH3 group. The expanded structure is complete. Next, I will draw the skeletal structure. Numbering the expanded structure, there are 4 carbons in the longest parent chain. I will draw those 4 carbons, and then there is a methyl group at C2. The skeletal structure is complete for A. For B, I have 2 CH3s in parentheses next to a CH. This tells me that the 2 CH3s are directly bonded to CH. Next, I have a CH2 bonded to an OH group. All carbons have 4 bonds, so we did not have to add any double or triple bonds. The expanded structure is complete. Next, I will draw the skeletal structure. Numbering the expanded structure, there are 3 carbons in the longest parent chain. I will draw those 3 carbons, and then there is an OH group at C1 and a methyl at C2. The skeletal structure is complete for B. Draw all structural isomers with the formula C4H10O. Label their functional groups. Structural isomers have the same molecular formula but a different connectivity of atoms, and the easiest way to know that you did not repeat a structure will be to write down the name for each structure. Structural isomers will have the same amount of carbons, hydrogens, and other atoms, but different names. To start, we can determine the degrees of unsaturation to know how many single bonds, rings, double bonds, or triple bonds we can have in the structure. For degrees of unsaturation, the formula will be 2 times carbon minus hydrogens minus halogens plus nitrogen plus 2 divided by 2, and we ignore oxygen and sulfur. For 1 degree of unsaturation, the structure could have a double bond or a ring. For 2 degrees of unsaturation, the structure could have a triple bond, 2 double bonds, 2 rings, or a ring and a double bond. As you continue to have a larger amount of degrees of unsaturation, you can have any combination of double bonds, rings, and triple bonds. For this formula, we have 2 times 4 minus 10 plus 2 divided by 2 to equal 0 degrees of unsaturation. So there will only be single bonds in the structure. Next, we can think about what functional groups could be created with the atoms that we have and the degrees of unsaturation. For 1 oxygen, with all single bonds, we can make an alcohol or an ether. Once we start drawing the isomers, start with the longest carbon chain possible, and then take off 1 carbon at a time to make substituents at different positions. Once that substituent group has been placed at every position possible to make a new name, take off another carbon and repeat the same steps. Starting with alcohols, I can have a 4-carbon chain with an OH group at C1. This will be called 1-butanol. Before changing the carbon chain, I can place the OH group at C2 to make 2-butanol. If I tried to put the OH group at C3 and C4, we would just start numbering from the opposite direction, so these compounds would not have new names. Next, I can use 1-butanol and take off a carbon to make a methyl substituent. The methyl substituent cannot be placed on the ends because this would just make the parent chain longer. So there is only one middle carbon to put the substituent on. The name of this compound would be 2-methyl-1-propanol. Next, I can do the same thing with 2-butanol. Taking off a methyl and putting it in the middle will give us a new compound called 2-methyl-2-propanol. These will be all of the alcohol compounds we can create. Next, we can move to ethers. I can put oxygen in the middle with 2 carbons on either side to create the compound called diethyl ether. Next, I can take off a carbon from one side and add it to the other side to make 1-methoxypropane. Next, I can change the attachment of the OCH3 group to make it 2-methoxypropane. These will be all the constitutional isomers for C4H10O. For the carbon in each compound, state whether it is sp3, sp2, or sp hybridized. For hybridization, if a carbon has 4 domains, it is sp3 hybridized. If it has 3 domains, it is sp2 hybridized. And if it has 2 domains, it is sp hybridized. For A, CH4 has 4 domains, so it is sp3 hybridized. For B, C1 has 3 domains, so it is sp2 hybridized, and C2 has 3 domains, so it is also sp2 hybridized. For C, C1 has 2 domains, so it is sp hybridized, and C2 has 2 domains, so it is also sp hybridized. Provide the IUPAC name for each. For naming, we will first find the longest parent chain of carbons, and then number the parent chain to have lowest numbered functional groups, then double bonds, then triple bonds, and then substituents. For A, the longest parent chain is 4 carbons, all single bonds with no substituents. All single bonds will have the ending A and E, and the prefix for 4 carbons is but. The name will be butane. For B, the longest parent chain is 4 carbons, all single bonds with a methyl at 2. The name will be 2-methylbutane. For C, the longest parent chain is 2 carbons with an OH group at C1. OH is an alcohol with an ending of OL for the functional group. The name will be 1-ethanol. Which compound would be more soluble in water, CH3OH or CH3CH3? For solubility, like dissolves like, meaning the compound with the most similar intermolecular forces will be most soluble. Water has hydrogen bonding due to its 2 OH groups. CH3OH also has hydrogen bonding due to its 1 OH group, and CH3CH3 only has dispersion forces and is nonpolar. CH3OH and water both have hydrogen bonding, so CH3OH will be more soluble in water due to those similar intermolecular forces. Rank these compounds from most acidic to least acidic. When comparing groups that have different functional groups, it can be best to use pKa values, but we can also compare the stability of their conjugate bases. For pKa values, CH3OH has a pKa value of 16, CH4 50, and CH3COOH 5. The lower the pKa, the stronger the acid. CH3COOH will be the most acidic, then CH3OH, then CH4. If we wanted to compare the stability of the conjugate bases instead, we will remove a proton from each. CH3OH's conjugate base will be CH3O-, CH4's conjugate base will be CH3-, and CH3COOH's conjugate base will be CH3COO-. Comparing the atoms with a negative charge, the 2 compounds with O- will be more stable because oxygen is more electronegative than carbon. This will make CH3- the least stable conjugate base and the least acidic. Comparing CH3O- and CH3COO-, CH3COO- will have resonance, so it will be more stable, and CH3COOH will be the most acidic. The ranking will be the same as what we saw for the pKa trend. CH3COOH is the most acidic, then CH3OH, and then CH4. For each carbon atom, classify as primary, secondary, tertiary, or quaternary. A primary carbon is a carbon that is bonded to only one other carbon. A secondary carbon is bonded to two other carbons. A tertiary carbon is bonded to three other carbons, and a quaternary carbon is bonded to four other carbons. For A, the NCH3s are only bonded to one other carbon, so they are both primary. For CH2, it is bonded to two other carbons, so it is secondary. For B, the CH3s are only bonded to one other carbon, so they are all primary carbons. For C, it is bonded to four other carbons, so it is a quaternary carbon. And for CH2, it is bonded to two other carbons, so it is a secondary carbon. Draw the most stable Newman projection for butane looking down the C2-C3 bond. First, I will draw butane's skeletal structure and number the parent chain. Butane has 4 carbons. We will be looking down the C2-C3 bond with C2 in front and C3 in the back. I will add the wedges and dashes to C2 and C3, and the hydrogens to those wedges and dashes. Looking down the C2-C3 bond from the right, when I turn the structure, the wedges will be on the right and the dashes on the left. C2 will have a CH3 group at the bottom and 2 H's at the top left and top right. C3 will have a CH3 group at the top with 2 H's at the bottom left and bottom right. The most stable Newman projection will have the largest groups on C2 and C3 anti to each other. The methyls are the largest groups, and in the present Newman projection, they are anti to each other, so this is the most stable Newman projection. To draw resonance structures, we want to look at patterns. The patterns that we can use for resonance structures will be a lone pair next to a pi bond, next to means separated by a single bond, and pi bond means double bond or triple bond. A lone pair next to a C plus atom, a pi bond next to a C plus atom, a pi bond directly connected to an electronegative element, O or N, and pi bonds going all the way around a ring. For acetate ion, we have a lone pair next to a pi bond. When we draw resonance structures, we do not want to break single bonds or have more than an octet. To keep each element's octet intact, we need 2 arrows for this pattern. The first arrow will show the lone pair on the negatively charged oxygen moving down to create a double bond, and the second arrow will show the double bond being pushed up to create a lone pair on the oxygen it was connected to. These will be our 2 resonance structures.